Alright, so this is our AP Chemistry Chapter 9 lesson video. It's part 2, and I'm going to cover section 9.3 through 9.5. And so again, a lot of this is going to be review from what we learned in Honors Chem, but there will be some little new pieces of information as we go. So remember that bond polarity is a measure of how equally the electrons in a bond are shared between two atoms in the bond. So remember, if it's two atoms that are the same, they'll have the same electronegativity or the same pull on those electrons, and we say that it's nonpolar. But if one has a greater electronegativity than the other, that electron will pull the electrons more, and so then you get a partial negative and partial positive side, and we say it's polar or has a dipole moment. So what we're going to talk about is in molecules when dipole moments sometimes can cancel out. So for a molecule that consists of more than two atoms, the dipole moment depends on both the polarities of the individual bonds and the geometry of the molecules. So bond dipoles and dipole moments are vector quantities. A vector just has a magnitude and direction. So for example, when we look at something like water, it has a bent geometry. And so when you look at a hydrogen-oxygen bond, you have a dipole moment that points towards oxygen. Well, you also have one that points towards oxygen in this case. So if you combine the two vectors, in general, our dipole moment points up towards the oxygen. However, in something like carbon dioxide, that CO, the dipole moment points towards the O. Well, on this one, it also points towards the O. So because this is linear geometry, they actually cancel out because they're in opposite directions and equal magnitude. So even though this molecule contains polar bonds, the molecule itself is nonpolar. So you have to use the geometry to determine if the dipoles cancel out or not when you're determining if an entire molecule is polar. So the overall dipole moment is the vector sum of its bond dipoles. If the dipoles are of equal magnitude but in opposite direction, then they cancel out, making the molecule nonpolar. So this is just another example of the one that I just showed you. So since they're equal in magnitude and opposite in direction, this molecule overall is nonpolar and has no dipole moment. But each bond would have its own dipole moment. They just cancel. So if the dipoles do not cancel out, then the molecule is polar. Be sure to consider the shape before deciding polarity. So for example, here NH3, it would have a lone pair up here. So it's going to have a trigonal pyramidal shape. And so in that case, when all of your dipoles point towards the nitrogen, there is an overall dipole that points upward. So this molecule is polar. However, something like BF3, if you look, all the dipoles are pointing in opposite directions of equal magnitude, and so they cancel out. So this molecule would be nonpolar. And the same thing happens here. Okay, all of the dipoles cancel because they're opposite and equal in magnitude, so this is nonpolar. One thing that could happen though is if the atoms aren't all the same, then you could still have a dipole moment. So in this case, a CH bond is barely considered polar. It's pretty much considered nonpolar, but it's slight polarity there. But a CCl bond, there's a dipole moment. And so there's no dipole moments down here to cancel them out. So this molecule would be considered polar. So it says, predict whether the following molecules are polar or nonpolar. So we'll look at this one together. So first we have to draw the molecule and decide the geometry. Alright, so Br has 7 valence electrons and Cl has 7 for a total of 14. When I have two atoms, I really only have one option for how to bond to them. So I have Br and Cl. Br has 2, so it needs 6 more. Cl has 2, so it also needs 6 more. So I'm allowed 14, 2, 4, 6, 8, 10, 12, 14. There's no other option of how to draw this, so this would be linear. And so if you look at a periodic table, remember F is the most electronegative element on the periodic table. Cl is closer to F than Br. So Cl would be the partially negative, Br would be the partially positive, or I could draw my dipole moment pointing towards Cl. So since there's no other dipole moment in the opposite direction to cancel it out, this molecule would be polar. So let's look at SO2. So S has 6 valence electrons. O has 6 times 2 for a total of 18 valence electrons. So since S is the single atom, it's going to go in the middle. So I bond my two O's. Ooh, I'm getting close to that negative right there. So O has 2, so it needs 6 more. O has 2, it needs 6 more. S has 2, 4, so it needs 4 more. But the problem is, on the lot of 18, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have 2 extras, which means I need 1 more bond. And so of course this is going to have resonance because it could go on either spot. So once I add that bond, I erase a lone pair off of each atom that touches the bond. But the resonance is not actually important in this case, so I'm not going to draw both structures, but the shape is. So see, right now it appears that it's linear, but I see there are 3 domains. So 3 domains doesn't make linear, okay? Because remember, that lone pair is going to balloon out, and it's going to keep those bonds away from it. So it's actually going to look like this. So the shape would actually be bent, the molecular shape. All right, so when you look, remember, N, O, and F are the 3 most electronegative elements on the periodic table. So my dipole is going to point towards the O's. And so see, there's no dipole pointing up to cancel them out. So in general, our dipole moment, like our net dipole moment, is downward towards the O's. So since nothing cancels out and there is a net dipole, this would also be polar. All right, so let's look at SF6. So S has 6 valence electrons. F has 7 times 6 for a total of 48. So S is going to go in the middle. And I'll put all my F's around it. Each F, I'm not going to show you every one of them, each F can have 6 more electrons because it has 2 from the bond. And then S already has 2, 4, 6, 8, 10, 12, so it definitely doesn't need any more. And so then if you count, it is 48 total. All right, so F is the most electronegative element on the periodic table, so all of my dipoles are going to point outward to the F's. So what I want you to notice is all of them point outward, so they're all going to cancel out because they're in opposite directions in equal magnitude. Okay, so because they all cancel, this would actually be nonpolar. So this would be an example of a nonpolar molecule that has polar bonds in the molecule. Okay, because all of those dipoles cancel. So you just have to look at the geometry on these, because that'll tell you, like for example, if you thought that was linear, you would have thought the dipoles canceled. So you got to be careful of those shapes. And so the lone pairs are what makes a difference on these. All right, so you try the next 2. You're just deciding is it polar or non-polar, and then we'll look at them together. So I'll assume you paused the video and already tried it. So we have NF3. So N has 5 valence electrons, F has 7 times 3. So 21 plus 5 is 26 valence electrons. N's going to go in the middle. I'm going to bond my F's. And so each F has 2 right now, so I'm going to give them 6 more. And then N has 2, 4, 6, so I'm going to give it 2 more. And then if you count, that's 26. I'm not going to make you watch me count. So I need to look at that geometry before I start deciding, are my dipoles canceling? All right, so I have 1, 2, 3, 4 domains. 4 domains makes tetrahedral. Okay, so I balloon my lone pair up. I'm going to pull one of my F's down here, and then I do one coming out of the board and one going back into the board. Okay, so F is the most electronegative element on the periodic table, so my dipoles are going to point downwards to all the F's. So notice there's no upward one to cancel out. Like when they cancel, you have to have them out in all directions. Okay, so I'm going to have a net dipole pointing down towards my F's. So this would be polar because they don't cancel out because of that lone pair. The lone pairs are usually what will cause it to not cancel out. Alright, so hopefully you got that one right. Now let's look at BCl3. So the second I see B, I need to think, whoa, wait a minute, that's an exception to the rule. B normally will only form 3 bonds or surround itself with 6 electrons, whichever way you want to remember it. Okay, so B has 3 valence electrons to start with. Cl has 7 times 3, so 21 plus 3 is 24. So B is going to go in the middle. So I'll bond all my Cl's. Cl has 2, so I'm going to add 6 more to each one. And then normally I'd add 2 more to B, but I already know B is an exception. And so in this case, it can't have 2 more. And so if you count, I do have 24. So I have 3 domains. 3 domains doesn't make the shape of a T. Remember, 3 domains is going to end up looking like this. We're going to have 120-degree bond angles here. Just like that. Okay, so CL is closer to F than B is, so all of my dipoles are going to point towards my CL. And so notice they're all in an equal magnitude and opposite direction, so they are going to cancel. And so that makes this molecule nonpolar. Just like that. Okay, so that's where you got to be careful, because these molecules seem like they would have the same shape, NF3 and BCl3, because they seem similar, and they are. But the thing is, boron doesn't normally get a full octet, and so that's what makes borons cancel and not nitrogens. All right, so hopefully you got both of those right. All right. So 9.4, we're going to start talking about hybridization and that type thing. So in the Lewis theory, covalent bonding occurs when atoms share electrons. In the valence bond theory, we visualize the buildup of electron density between 2 nuclei as occurring when the orbitals of the atoms overlap. So once we have the overlapping, so you see this is an S and a P that are overlapping. These are 2 S's overlapping, or 2 P's. So that little overlap is what we consider as the bonding area, or the electron domain. The overlap of orbitals allows 2 electrons of opposite spin to share the common space between the nuclei, forming a covalent bond. The bond length of a covalent bond corresponds to the minimum of the potential energy curve. Okay, so y'all, all of the potential energy curves for 2 elements look similar to this. So the actual bond length will happen at the minimum energy. Okay, because what happens is if you put them too close together, the 2 nuclei are going to repel each other. They don't want to be that close. But if you keep them too far apart, then they don't get a chance to attract each other. So this is like the sweet spot. So what's different about this curve for other elements? Well, depending on the strength of the bond, that depends on how high or low the minimum is. A stronger bond will have a lower energy because, of course, remember, low energy is more favorable thermodynamically. So a weaker bond might have a higher energy. And then on this, when we're talking about the distance, it depends on the radius of the atoms. Larger atoms might have their minimum further in this direction, and smaller atoms would have their minimum further in that direction. Now, of course, you can't get any smaller than hydrogens, but if this was something else and we were doing a smaller atom, it would be in that direction. But otherwise, they tend to follow the same curve. It just depends on where is the minimum, so you know how strong is the bond, and what is the bond length, so what is the radius. The other thing that will make a difference is how many bonds you have. So like if you're comparing a single bond to a triple bond normally is of course harder to break, so its minimum might be lower, but a triple bond is also shorter than like a double or single bond, so it might be over this direction some too. So I will tell you that I like to ask questions about giving you the curve for one set of elements and then asking you to draw what a curve for other sets would look like. So we'll practice those in class. So, section 9.5, hybrid orbitals. So let's get into this hybridization. To explain geometries, we assume that the atomic orbitals on an atom mix to form new orbitals called hybrid orbitals. The process of mixing atomic orbitals is called hybridization. The number of hybrid orbitals must equal the number of atomic orbitals. So if I start with 3 atomic orbitals, I must get 3 hybrid orbitals. So here I have 1 s and I have 2 p orbitals. So notice I have 3 hybridized orbitals. I can't start with 3 and end with 4, or start with 3 and end with 2. I always have to have the same amount. So how does this happen, and why do we think it happens? Well, it's all based on the electron configuration. So if I'm trying to make BeF2, we know these bonds are identical. There's nothing different about this bond and this bond. They must be identical. So if you look at the electron configuration, F ends in 2p5, so clearly it needs this electron right here to be able to share in order to have the full octet. This shows that F can bond by filling its 2p sublevel. However, if you look, Be on the other hand, it has 1s2, 2s2, and it has 3 empty 2p orbitals. So since Be has no unpaired electrons, it shouldn't really want to form bonds. So one of its electrons is kind of promoted to a 2p orbital. Okay, so here I'll go back. You can clearly see how F needs the other electron to finish off that pair of electrons. But like I said, Be, they're already all paired, so why would we all of a sudden start adding there? Because they share to get those paired electrons. So like I said, one of them is promoted. But the problem with this is a 2s orbital is not the same as a 2p orbital. So if that was what happened, then the two bonds should not be the same. So however, the arrangement would make the two BeF bonds would not make the two BeF bonds equal, because one would involve an s orbital and one would involve a p orbital. So that's where we get the hybridization from. So we can form two hybrid sp orbitals, which have two lobes like a p orbital, but one lobe is much larger than the other. So this is what a normal s orbital looks like. It's a sphere. The p orbital has that dumbbell or teardrop shape, but they're the same size. So we have two orbitals that we're hybridizing, so we get two hybrid orbitals. So they're similar to a p in the fact that they still have two lobes, but they're similar to an s in the fact that only one lobe is larger. And then this is just them overlapping, like you can see where the nucleus is. And so what we do is we say, okay, well these are going to be sp orbitals, so now they're the same, and then we still have our normal 2p orbitals left over. So the remaining 2p orbitals remain the same. So the hybrid orbitals and bonding in BeF2 would look like the following diagrams. So it has sp hybridization, because we took one s and one p and hybridized them to make the bonds equal. Whenever we mix a certain number of atomic orbitals, we get the same number of hybrid orbitals. Each of the hybrid orbitals is equivalent to the others, but points in a different direction. So all the hybrid orbitals must be the same. That's what makes all the bonds the same. Thus, mixing one 2s and one 2p orbital yields two equivalent sp hybrid orbitals that point in opposite directions. So that's what we just saw with the BF2. So now let's, or the BeF2. So now let's look at BF3. So again, F is all ready to form one bond and get that last unpaired electron taken care of. So this shows that F can bond by filling its 2p sublevel. However, B has some paired electrons and has one lone electron. So it seems as though B should only be interested in forming one bond to get that other pair, but we can clearly see that it's going to form three, and all of these bonds are identical. So we're going to have to do some hybridization. So since boron has one unpaired electron, it should only form one bond. So one of the electrons from 2s is again promoted to 2p to allow for three bonds. So see, now we have the opportunity to do one bond, two bonds, three bonds. But this would not make the bonds equal, because of course one would be made by an s orbital and two would be made by p orbitals. So that's where the hybridization comes from. Now this hybridization will be different because we're using one s and 2p, so we call that sp2 hybridization. So we can form three hybrid sp2 orbitals, which have two lobes like a p orbital, but one lobe is much larger than the other. And so again, these are all three going to point in opposite directions. So see, now if we change those to sp2, because it's made of one s and 2p, then that allows for us to make a bond for each of them. And then we still have that 2p remaining as just a 2p orbital. So the hybrid orbitals and bonding in BF3 would look like the following diagrams. Okay, so again, there's our hybrid sp2 orbitals, but then we still have that remaining 2p orbital that just stays the same. Alright, so last one we're going to look at is CH4. So CH4, hydrogen, has one lone electron. It needs to pair up, so it makes sense that hydrogen would want to bond by filling its 1s sublevel. Carbon, on the other hand, has two unpaired electrons. So it seems as though carbon would only want to form two bonds, but we can clearly see that it forms four. So what are we going to do? We're going to take one from that 2s and promote it, just like we've been doing. Okay, so we promote one from 2s, So now we can form 4 bonds, but remember, they're not going to be the same because we have 1 from S and 3 from P. So if we hybridize them, we have S and 3 P's, so we're going to get an sp3 hybridization. Okay, so we have 4 hybrids, so we have sp3, so see we have 1 S and 3 P's that we mix together, and they're all going to point opposite directions. Notice it makes a tetrahedral shape. So then it looks like this. So now carbon is ready to form 4 equivalent bonds with its sp3 hybridization. The hybrid orbitals and bonding in CH4 would look like the following diagram. So again, they're going to point in all opposite directions, and that's where we get that tetrahedral shape from. So the good news is, if that was a little confusing for you, on the AP exam, they don't usually seem to ask you like to explain how hybridization works. They just want you to be able to know what it is. And so it's totally based on the electron domain geometry. If it is linear electron domain geometry, it is always sp hybridization. If it is trigonal planar, or 3 electron domains, it's sp2. 3 domains, spp. And if there are 4 domains, or it's tetrahedral in shape, then it's SPPP, or SP3. So really you just need to know how many electron domains there are, and then you can figure out the hybridization. So let's look at one together. So it says, indicate the hybridization of the orbitals employed by the central atom in NH2 negative. See, y'all, don't let the weird wording throw you off. They're just asking hybridization of NH2 negative. So N is 5, H is 1 times 2, and the negative means we add 1. So we have 5 plus 2, which is 7, plus 1, which is 8 valence electrons. All right, so I'm going to bond everybody. So I have my N, my H. Remember, H doesn't need anything else. H follows the duet rule. Nitrogen has 2, 4, so I give it 4 more. 2, 4, 6, 8, so I'm good to go. And then keep in mind, though, y'all, I need that negative. Now, a lot of times you would look at that and say, oh, well, that's linear. It must be SP. But you know this isn't linear. There are 4 domains. So what it would actually look like would be this. We balloon those 2 lone pairs out, and it's going to bend those hydrogens down. So my shape is actually bent. Or my electron domain would be tetrahedral. And you don't have to draw it 3D to tell that. Once you see 4 domains, that's how you know it's sp3. 4 orbitals, 4 domains. So if I'd had 3 domains, I would have called it sp2. Okay, so it's just about the shape. So on these, you don't technically have to draw the 3D shape to figure it out. I just usually draw it just to make sure I know what you're doing. Okay, so y'all pause it. Try this one. You're doing hybridization for SO3 negative 2. I'll assume you paused it, so let's look at it together. So S has 6, O has 6 times 3, and the negative 2 means plus 2 more. So I have 18 plus 2, which is 20, plus 6, which is 26 valence electrons. All right, so I put my S, put my 3 O's. O has 2, so it needs 6 more, so I'm going to do that to all 3 of them. S has 2, 4, 6, so it needs 2 more. See, y'all, you got to get to where you can at least draw the flat shapes pretty quickly, okay, because you don't want to have to waste a lot of time on the AP exam over drawing flat shapes. All right, so once I count up, it is 26, and even though I technically don't have to waste time putting the brackets because that's not part of the question, I'm going to. But see, that's something on the AP exam you might want to skip and not necessarily waste time doing that. All right, so again, this time I'm going to show you how I'm not even going to waste time drawing it 3D. I can see there's 1, 2, 3, 4 domains, so that's sp3 right there. And you don't even have to waste time redrawing it as trigonal pyramidal. Okay, once I see 4 domains, I know it's sp3. All right, so hopefully you got that right. Alright, so that was it for this video. So the only new part is, because we learned hybridization in Honors Chem, but the explanation behind it, that part might have been kind of new. And then I don't think we did that potential energy versus internuclear distance graph in Honors. But hopefully none of this was too tricky. And just make sure, again, you get really fast at drawing Lewis dot structures and you really know those Vesper shapes.